Okay, let's begin. Optimization, those were the days.
Oh no. Absolutely
Such fond memories.
No.
Sometimes it's funny how math that used to give you nightmares, all of a sudden it's like, man, I wish I could go back. I'd just stay there. I would be king of the world. So, let's actually continue. Last time, we looked at how to construct something called Fourier series. So f of x is a 2L periodic function. Then you may write f of x as a series of sines and cosines, namely in this form, a naught over 2 plus the sum from n equals 1 to infinity of a n cosine n pi x over L plus b n sine n pi x. Now, of course, to make a series fit a particular function, and of course we'll have to check whether it converges or not, we need to know how to find the coefficients. So where a0 is 1 over L, integral from minus L to L f of x. N is 1 over L integral from minus L to L of f of x cosine pi x over L. And your Bn is equal to 1 over L integral from minus L to L of f of x times the sine. So we painstakingly derived that last time. You don't really need to know how to derive it, you just need to know that that's how you express a function as a Fourier series. Now for us, we're going to look at functions with period 2L, even though technically you can kind of always do this with almost anything. So the motivation here was, of course, well, I'll talk a little bit more about motivation later, if not at the beginning of next class. But we saw how power series were really cool and they made a lot of things work out nicer than normal. So we kind of wanted to do the same idea with periodic functions specifically. So instead of thinking of it as an infinite polynomial, just think of it as an infinite sequence of cosines and sines, because those are very nice periodic functions that we know of. And an added benefit to the Fourier series, which we're not going to talk about because technically it's not in our syllabus, because technically you guys are considered engineering students. So we don't really talk about convergence or the theory that much, but the benefit of this is that when it does converge exactly to the function, it will actually converge faster than a Taylor series on average. And things that converge faster is good. It means you can use less terms of a series to fit a function nicer, right? So if you can ever use 5 terms instead of having to use 100 terms, that's always good. That's less information, less computation, and it all adds up. So these guys are really very efficient, at least compared to something like a Taylor series, when you are trying to model a periodic function. So we call that a Fourier series. And we derived that last time, so right now I just want to actually do an example. Then I'll tell you about something else, and we'll do some more examples. So here is the example. The f of x equals 2 from 0 to 1, and it is 0 from minus 1, 0. Is periodic. And of course, let's find these Fourier series. So here we were given a function. We're told just one part of it, the principal period, and we actually want to expand it as a Fourier series. I want you to note, you don't have to draw the picture, but I'm just going to draw it so you can actually see what we're thinking about here. So, we are talking about on the interval from, say, -1 to 1. And it says on 0 to 1, we're just a constant function too. Where it can be equal here, but there's an open circle there. And then on -1 to 0, use a different color here. So that's one part, and on the other part, it is actually just 0, so where it's equal to 0 here, and not equal to 0 there. So that is the principal period, and so of course the idea is, we're thinking of this thing being repeated. Pretty much every 2 pi. I'm just going to have copies of this thing. Right, going on forever. So this is going along the entire x-axis, and that's the pattern. So now we want to get to a Fourier series. So one iteration might look like so that's going to be, huh?
We're going to be penalized for making the sound when we're taking the test.
No.
No, well, you don't have to draw it, so you shouldn't be making any sound. But yeah, if you were drawing it, that if you don't make a sound, I'd have to deduct the pointers. So you draw it.
Is that a discontinuity there, or is it?
Yes, so technically it's a discontinuity, but the function itself is discontinuous here. There's a jump discontinuity, but the theory says the Fourier series will actually jump up and pass through the average value. So it'll connect a dot to a dot here whenever there's a discontinuity. It'll average the value of any jump discontinuities. So your Fourier series just thinks of it's running along this curve, but it'll always going to jump through these points. So that'll be some approximation to our function.
So if we had something, the function of something was like 1.5, I'm sorry, 0.5, it would find that.
Yeah, so this is going to happen at the level. This is at level 2, so this will happen at level
That's
1.
Okay.
Yeah, it'll average this. The output here is 0. The output there is 2. 2 plus 0 all over 2 is 1. So it'll definitely pass through the value of 1. Now, so that's kind of the situation. How do I find that red curve? What is the series that represents that red curve? That's what we want. And of course, the more terms you take, the closer that red curve is going to fit those lines. So let's actually figure out what that is. So what we're going to do is, we know that our f of x is going to be equal to a0 to 2 plus 1 to infinity of a cosine n pi x over L plus bn sine n pi x over L. And here, L is equal to
2 over L? No. Negative 1 to 1.
it's actually equal to 1, right? It's the half the period. So we know that the period is 2, but we assume that the period of the function is 2L. So you just solve that equation for L, you get L equals 1. Okay? So L equals 1 in our equation. And so what we're going to have here is our A0 is going to be 1 over 1 times integral from -1 to 1 of the function. Now, what does that function look like? Well, it depends on what interval you're talking about. From -1 to 0, it will be the function 0. From 0 to 1, it is going to be the function 2. And so now you can kind of notice that for all future terms, I don't really have to care about the -1 to 0 part. In this case, I just have to care about the 0 to 1 part. So that's going to go off to 0. This is going to be, well, 2, right? Get 2x plug in 1. So a0 is just 2. And I'm going to go and find the an. Well, the an is going to be 1 over 1 times integral from -1 to 1 of f of x cosine n pi x over L. Now, this is end up going to be from 0 to 1 because I know for the -1 to 0, it's just going to give me 0. So it's going to be 0 to 1 of 2 times the cosine of n pi x over L. But my L is 1. So now I want to integrate that. The integral of cosine n pi x.
2 sine n pi x over n pi.
Right, you divide by the coefficient, so it's 2 over n pi times that between 0 and 1. So if I plug in 1, what's going to happen here?
That's going to be 0.
And if I plug in 0, it's going to be 0. So all the an terms besides the first one, there's 0. So now I would find the Pn. My Pn is going to look like 1 over 1, integral from -1 to 1 of f of x sine n pi x over L, which is 1. That is going to be on -1 to 0, it's 0, but on 0 to 1, I'm now going to integrate this function. Integral of that is going to be -2 over n pi cosine n pi x between 0 and 1. And what's going to happen now? If I plug in 1, so this is going to be -2 over n pi of cosine n pi plus, if I plug in 0, I just get 1. 2 over n pi. Now,
I have a question.
yes,
Why is it with that one was the top one was sort of?
huh?
Now.
Okay.
I have a question. Are we assuming that n is always a discrete integer? And
Yes, n is always a positive integer, 1 and bigger. Right, the series starts at 1. So we're always assuming n is going to go through 1, 2, 3, 4, blah, blah, blah. So, that being said, what can you tell me about cosine n pi?
It's always
Negative one.
negative. It's negative or positive 1.
It's going to be negative or positive. What's the cases?
Ah, it's
When does it give you a positive one? When n is even, that's going to give you a positive one. So one thing you can notice is that if n is even, this is going to output positive 1, so you're going to have -2 over n pi plus 2 over n pi. So it will give you 0 on all the even ends, but on the odd ends, what's going to happen? Well, that's now going to give me a -1, which makes this positive. Added to that, I'm going to get 4 over n pi.
So when we're plugging in, say, like the 1 in for -2 over n pi cosine n pi x, we're not treating that like it's turning the whole thing into just 1, right? N pi are still.
No, I mean, it's a dx, remember. So I'm literally taking these numbers and plugging into the x only.
Okay, so we still have an n pi in there.
So there's still an n pi in there. So the n is a variable, but it's a variable with respect to the series, not with respect to the integral.
Okay.
So the integral, the variable is x. So we're plugging into the x here. But eventually we're going to take this expression and plug it into that series for the bn. So the bn is actually a function of n. right? And so that's what that's going to have. So what you notice happens here is that we will pretty much get that this function, if we represent it as a Fourier series, it will be a0 over 2. Our a0 was 2, so that's just 1 here. Plus a series of the ANs, they're all zeros once n is not 1, so there's no cosine part. And then the Bn, that's going to look like 4 over n pi times sine of n pi. And this doesn't work for all n's, it works for n odd. I mean, you could say it's for all n's, but another way to write this is you could say something like n goes from 1 to infinity, but instead of n, write 2n plus 1. 2n plus 1 x. Right? And that's only going to give you odds all the time.
When you miss,
We want to start what?
when you miss a term,
We would miss a term, make that minus. Now we catch everybody.
What about when n is even? Wouldn't it just be 1?
Huh?
When n is even, wouldn't it just be 1? Because the b of n is 0 when n is even. So wouldn't f of x be a piecewise function? When
No, this is always going to output an odd.
No, I mean over there, when b of n is always 0 when n is even, right?
Yes.
So wouldn't f of x also be a piecewise function for when n is odd? It would be that, and when n is even, f of x would just be 1.
the series would disappear.
Yeah.
Well, no, I'm not. This thing will never put an even number in this position.
He's
It'll never actually
he's saying that there's another part of the series which is 1 plus the summation of n is even. And that would be 1 plus the sum of a series that's always 0. So that then is 1.
I'm not sure what you're trying to say.
Anytime n is even,
Yes.
the series itself is always 0 when n is even, right?
Mm-hmm.
However, that's being added to a 1.
Yeah, which I took care of that separately.
Okay.
So it's taken care of here,
Okay.
right? And then I worry about the series as a separate thing, right? For the series, he only functions when the integer you're plugging in is an odd integer, so I can write it as 2n minus 1 instead. Because no matter what I plug in for n here, this is always going to give me an odd number.
Right.
So even if here technically you set n to be even, like 2 times 2 is 4 minus 1, it'll plug in 3.
Right.
So this is only plugging in odd numbers, because the evens are all zeros. I'm never going to actually have an even integer in this position, right? So odd integers, you can express them as 2n plus 1. Even integers, you can express them as 2n, right? That's the definition of what it means to be even. You're 2 times an integer. The definition of being odd, you're 2 times an integer, either plus or minus 1, depending on where you want to start. So for this particular example, were this on a test or a quiz, that would be your answer. This is the Fourier series.
We could write it as just the n is the n odd.
Yeah, this is also fun.
Okay, so now I have a question.
Mhm.
Why did we start from 0 to 1 if we have to go from -1 to 1?
Because technically we do go from -1 to 1, but on -1 to 1, f of x is 0. So it's 0 times the sine, blah, 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 plus this. Well, that's just going to be 0, so I'm just ignoring. Our function is 0 on this, on -1 to 0. So I just ignore that part. So technically it is there, I'm just not writing it because there's no point. That's wasting time.
It also makes sense in terms of the graph.
And it makes sense in terms of the graph. So the graph was just on the x-axis whenever we were in that region. It actually just gives us a non-zero value on half of it, on the 0 to 1. So, that's the first example. Other questions about this?
Are these generally going to be piecewise functions? I think you said something about that last.
It happens often. I wouldn't just say like, it's a general thing, like, I wouldn't be surprised if it branches off like this. Because I mean, you're always gonna have cosines and sines, which they hop up and down, so it's not strange to have a plus or minus 1. So, now, let's refine the theory a bit, because this was a relatively easy problem. Our function was a constant, right? So if our function was not a constant, and you're multiplying by a sine, then you're integration by parts, and it can get really messy. So, anything that will allow us to cut down on the computation that we're doing is good. This leads us into 10.4, where it talks about Fourier series for very particular kinds of functions. Even and odd functions.
I have a question about the Elmer.
Huh?
I have a question about the Elmer.
Yeah?
Just all of it. So there's like 4 or 5 sections that are titled EC or those extra credit homeworks, so it's just not part of the book.
No, they're not extra credits, it's just homework that you do. It's just that in web work, if someone, it's hard to change the title without having to reconstruct the whole, it's one of those programming things, like I couldn't change the title. So I think the person who created the homework, he assigned it as extra credit, but no, for you guys it happens. So, what do you remember about even functions? F of x is even means what?
Something with the axes.
They reflect over the y-axis.
It is symmetric about the y-axis. Computationally, this means f of minus x is equal to f of x. And this means symmetric about the y-axis. So for example, cosine is an even function. Because if you look on the right side of the y-axis, if you flip it over and take the mirror image, you actually get the left side. And it also tells you, if I put in an x here, and I get a certain y value, then the negative of that value will actually give me the same y value. That's what this means, right? Plug in the negative value, gives me the same as the positive value. So for example, a cosine is an even function. It is symmetric about the y-axis. Odd functions. So this means your f of minus x is the negative of f of x. These guys are symmetric about the origin. It's kind of a strange thing to say, but let me give you an example. The sine function is an odd function. That's odd. It's strange. No, it's not strange. It just means, oh, that's odd. Like that looks the same. But what it means is that if you take a positive x and it outputs a certain y value, then if you take the corresponding negative x, it will actually output the negative of that y value. So what happens is symmetric about the origin, meaning if you use the origin as a focal point or pivot point, then if you rotate around that focal point 180 degrees, the graph will lie on top of the other one. Another way to actually look at that is if you take the right side, flip it in the y, then flip it in the x, you get the other side. So that's what it means to be odd. Now, based on those definitions, the following is going to be true. We have that. Let's say f of x and g of x are functions. Then, if f is odd and g is odd, what does that tell you about their product, fg? If I have two odd functions and I multiply them together, what happens to the product?
It's also odd. No, it's even.
Huh?
Odd.
right?
I can't do it.
How does that
It
make?
does make sense.
Okay, how?
Two next, two odd, oh, I just thought odd is
Because with numbers don't work out.
Yeah,
Like
yeah.
if I take an odd integer times an odd integer, you get an odd integer. With functions though, it makes them even. The reason is, if I plug in negatives here, because they're both odd, they'll factor out the negatives, and then the negatives will just cancel each other, and you get the original function back, which is by definition even. Right? If S is even and G is even, then FG is even. The only time you get an odd is when one is odd and the other isn't. If F odd, G even,
Assuming.
or vice versa, then the product is odd. So one of them, only one of them have to be odd in order for the product to be odd. Why do we care? Well, when it comes to integrals, if F is even, then if you integrate from, say, minus a to a of f of x dx, we know a shortcut.
Let's do minus 2.
It's going to be 2 times
0 to 0.
0 to a of f of x dx. And if f is odd, then the integral from minus a to a of f of x is 0. Right? Because here, what's on the right side from 0 to a is going to be a copy of what's on the left side from negative a to 0. So you're really doubling the area, right? That's what happens if you integrate an even function. Whereas here, the right side, if that's positive, the left side is going to be negative, and it's going to be the same version. And so you'll have the areas canceling out. So we know that. For most people, they tell you that in like Calc 1 at some point, and you never see it until just now. I mean, you might use it every now and then in homework, but they don't really emphasize anything. But we have those properties. So what does that mean? So let's say I have a function that I want to find a Fourier series for. So let's say f is even, okay, in that situation. Then what would its Fourier series look like?
2 times,
My a naught is going to be, well, 1 over L times integral from minus L to L of f of x dx, which is just going to be equal to 2 over L from 0 to L of f of x dx. Because it's an even function. What about the an? Well, that's going to be 1 over L times integral from minus L to L of f of x times cosine n pi x over L dx. Now, cosine is even, and my f is even. So the product is therefore even. And so I'd be able to just do 2 over L times 0 to L of this function.
so f of x was odd.
Well, I'm gonna write down that. And when I get there, you can tell me. Okay. Now, what about the bn? Well, that would be 1 over L times minus L to L of f of x times sine n pi x over L. Now, your sine is an odd function. This guy is an even function, which means the product is odd. And I'm integrating from minus L to L. What's the answer going to be? They're all going to be 0. So if your function is even, the Fourier series will only have cosines in it. It will not have sines. Because the cosine is what's going to model the even part of the function, but the entire function is even. So we don't need the sines. The sines will contribute an odd function. So that's important. So if it's even, then you only care about the a's. Ignore the b's. And when you're computing the a's, you can actually just compute it on half the interval and double your answer. So we cut our work pretty much in half at this point, right? So the 2 integrals that we have to do anyway, we only have to do half of them, because plugging in 0 is usually going to be very easy. And we don't even have to worry about the b's at all. in a similar way, if I assume my f is odd, what's going to happen? Well, my a0 is going to be 1 over L times minus L to L of f of x dx. Integral from minus L to L of an odd function, well, that's 0. Not going to need to find the a. I do an, that's going to be 1 over L integral from minus L to L of f of x times cosine. Well, the cosine is even, this guy is odd, the product is odd, so that's going to give me 0. And,
Any odd products will give you 0.
yeah, and my bn, well, that's 1 over L from minus L to L of f of x sine n pi x over L. Well, now the function is odd, the sine is odd times odd, we're talking about functions, you get an even. So that's going to double up on me. So if your function is an even function, you only need to compute the a's. If your function is an odd function, you only need to compute the b's. Ignore the a's. And then your series would only have one type of trig function in it. It's either going to be all cosines or all sines. And you might have noticed that the example we just did last time, it was almost odd. Like there was a branch over here, but there was no lower branch over here. So it almost behaved like a sine, right? You know, so it's like there was a bulge here, but there was no bulge missing there. So we had one of the a's. We had the a0 existing, but I didn't need any of the others because after that, it sort of behaved like an odd function with a part of it sliced off. And so that's why we had the a0. But if the function was definitely strictly odd, we wouldn't even have the a0. We'd have just a bunch of zeros. So in summary, if f is even, then its Fourier series is going to be f of x equals a0 over 2 plus an cosine n pi x over L, where your a0 is 2 over L, 0 to L of f of x, and your an is 2 over L, 0 to L of f of x cosine n pi x. So there is no sine part to this function. And for that reason, whenever we have an even function, we call its Fourier series, it's called a cosine series. In this case. So here's a function, find this cosine series. It's just someone telling you, find the Fourier series, but only find the cosine parts. And even functions will behave like that.
But could a sine part still exist?
No, if it's even, the sine part is never going to exist.
So isn't it redundant for them to ask you to find the cosine series if it's the only one that actually exists?
Well, if you know it's even in the first place.
Oh, okay.
So that would be something you have to check. Like, so you just know, if it's, and sometimes I'll give you an example where you'll see the relevance of this. If f is odd, then its Fourier series, and in this case, it's called a sine series. So say, find the Fourier sine series of this function, or find the sine series for this function. Is f of x equals, there's no a's, so it just jumps right into the series. Where the bn is 2 over L, 0 to L, of f of x sine n pi x over L. So there are times times when you're given an even function or you're given an odd function, and if you notice that that's what you're given, you can just do half the work. There are other times when they would give you half of a function. They tell you, okay, here's one side of a function that we care about, expand it as a sine series. And basically what they're telling you is that construct the other side so that it ends up being odd. So sometimes you want to actually induce an even or an odd function for various reasons. So let's look at an example. Let's look at the previous function. So our f of x is 2 on 0 and 1, and they might say something like this. Extend f as an even function and find its cosine series. So there are times where we're going to want to actually force it to be one way or the other. So we know about half of it, and I just want to find the sine series component. So here, in this case, we are told this, and that's what we're given. Now what we want to do is to make sure that we are going to construct a series such that if I flip this over the y, I get the other part. So this, it'll just copy itself over here, like that. So we construct this. And so now, it's going to start actually copying that over and over and over. So as you can see here, it'll pretty much in reality create a constant function where it has holes every now and then. But the Fourier series is still going to be like wiggly along this thing. So it'll be a very small amplitude series. And it turns out that the equation of that series is going to only have cosines in it. So I want an approximation for this new function. So sometimes they give you half of it and they say, oh, extend it as an even series, find the cosine. Or they might say, extend it as an odd function, and you know that you'll actually write in -2 as the other side, so that it rotates around the origin and does this. And there are other times when, in applications, where you just know for this particular application, I care about the cosine series specifically. Or in this application, I care about the sine series specifically. And we're actually going to see something like that. We're going to see an application where it just makes sense to only look for the sine series. Just ignore the cosine series. So we'll pretend it's an odd function regardless. So, once they actually tell you that.
I have a question.
Yeah.
We're assuming that the amplitude is extremely small, right? We're assuming the amplitude is extremely small for it to emulate those.
Yeah, it'll be extremely small.
Could we also make an assumption that the period is infinitely large? So it'd be a very large, like.
No, we wouldn't make that assumption because the period is just going to be determined by these punctures that we have. So these little punctures are going to happen, and that's when we say, okay, we're done with one period.
But wouldn't the Fourier series fill it in with the average value? So the punctures would disappear.
Yeah, but it's still, there's a natural break here. You know what I mean? It's like you're attaching something at that point. So what we would do here, once they told us that we want to extend as a cosine series, so pretty much I'm going to ignore these. And I'm just going to jump into finding the a's. So to find a0, I'm going to use 2 over L times 0 to L of f of x dx, which in this case, again, it's 2 over 1, L is 1 in this case, of f of x. So in this case, that's going to give us what? 4. And for the a and n's, I'm going to be 2 over L times 0 to L of the f times the cosine. So that's going to be 2 times the root of 0 to 1 of 2 cosine n pi x over L dx. So that is going to be
2 sine n pi x.
so that's one.
Yeah, that should be.
So it's 2 over n pi sine of n pi x between 0 and 1. All of that times 2. What's going to happen?
It's gonna be 0.
It's going to be 0. So something that makes complete sense by looking at the picture. What did you end up finding? F of x equals 4 over 2 plus the series of 0. It's just 2.
Wow.
Makes total sense, which
Yeah.
we're right. It's just going to start filling in those holes.
Yeah.
You're just going to have a constant function. Funny how that works.
Yeah, because that's
Like, yeah, from
saying.
drawing the picture, yeah, obviously it's just the constant function y equals 2, isn't it? Go through the Fourier, it gives you that. Yeah, that's a perfect fit right there. Perfect fit with one term.
I feel like math at this point just got super complicated that we have to go back to like basic stuff. It's just like back to kindergarten.
Yeah.
I swear.
Yeah.
Oh, everything we do is just like, oh yeah.
You know when you come far when calculus is like kindergarten. Yeah, it's like we're going back to kindergarten. Like even functions and integral over a balanced interval. It's like we're in kindergarten here.
Fourier, I'm sure it was.
Exactly, yeah, bro, it's retarded. You know, like you see those kids that are like, oh my gosh, I'm like, I do it in my head.
Let's do a more interesting example.
Oh no.
Wait, can we do one without a tangent?
Without
Like a random graph?
without no, we're not going to do any without.
Why not?
So here's an example. So something like what I would put on a test would be like, what was it, solve 11, and I forgot the problem. Anyway, it says, the actual number, but it's on 2011. It says find the sine series for f of x equals x times 1 minus x on 0, 1. So again, notice that it gives you half an interval, it only gives you to the right side of 0, where for our theory, we assume it goes to the left and the right side of 0. So they're saying, okay, that's our function, extend it as an odd function. So you don't have to draw it, but the picture here, for those of you who are curious. No, not curious, it's fine. What does this look like?
It's like a negative x squared,
Yeah, so
and then
intercepts,
0 and 1.
it intersects at 0 and 1, and just upside down, right?
Yeah.
So it looks like that. And now it says, find the sine series. What that means is, it wants us to extend the other side to look like
This is a
this.
sine function.
And it'll look like a sine function, but not exactly a sine function. And it is a polynomial after all. Right, so if we continue this, well, it will give us that, and then that. So it'll look like a sine function, but it won't necessarily decrease or increase as quickly as sine does. But yeah, it's like you're creating an almost a pseudo sine function. Which, it's fitting that you'd only use sines to represent something like that. So, what would the series actually look like?
There's no way not in
Yeah, they have 0, 0.
So once they say the word sine series, that means ignore the A's, only focus on the B's. Right? So if you're not paying attention, you're not reading, you're going to do like triple the work. So because it says sine series, I'm going to ignore the A's. that includes the A0. So I'm immediately going to jump into the B ends. That's going to be 2 over L integral from 0 to L of f of x sine. L in this case is 1, because that's the length here. So it's 2, 0 to 1 of x times 1 minus x times sine of n pi x. Okay, how are we going to integrate that?
By part.
By parts. I would 0 to 1, I'll probably look at that as something like 2x minus 2x squared times the sine of n pi x. And maybe just do like a tabular thing.
2 minus
So 2 minus 4x
and then minus 4.
minus 4 and then 0. So you stop when you see the 0. And then here you're going to keep integrating that. So that is 1 over n pi times minus cosine. Then you have minus 1 over n pi squared times sine. Then you're going to multiply it by the negative again, so it becomes positive n pi cubed times cosine. So we are going to add this product, subtract that product, add this product.
It's just got complicated.
What did I say?
Oh my god.
No, it's integrated by parts. It's like kindergarten.
Yeah.
Sure. Okay, now that's pretty great right there.
This is like first grade. Yeah.
Oh, like,
So this is in Calc 2. So we are going to have minus and then this is going to be plus and then we're going to have minus and all of that between 0 and 1.
So the green lines are.
I'm adding.
Oh, add.
So the green lines means after you do the product, you take a positive times it. And then you take a negative times the product. And then you take a positive times the product.
And
So
then
you
across-
multiply this, there'll be a negative sign, multiply by a positive sign, it stays negative. You multiply across this, there's going to be a negative sign, multiply by a negative sign, it turns positive.
Okay.
So that's where this is coming from.
And then the 0 you just multiply, right?
Yeah, technically there comes a point where you have to go back here and then integrate that term, but that's just going to be the definite integral of 0, so you ignore that part.
No, wouldn't it just keep on going forever with zeros? So it doesn't really matter?
No, you stop at the last step.
Yeah, you stop at 0.
No.
You stop when it hits 0, or this row is just a repeat of the original, times a constant probably, or you get to a row where you realize that integrating across the line is going to be super easy. But for the last, so technically this would be minus the integral of 0 times,
Which is just 0.
over n pi cubed dx, which is 0. So we always ignore that part. But technically there's the tail end of the integration by parts is an integral.
So let's say we were desperate, we wouldn't be able to remember that. Is there any way we could do it with?
No, you can do it by parts. You'll need it like 3 times. You need integration by parts 3 times.
Jesus.
So you can do it the old way. But
Nah, I'm good.
The old way is the same as this, it's just.
no, you'll get to the same answer, just a lot slower.
Yeah.
No, trust me, you'll get scared after the first one. You're like, oh, what the hell am I doing wrong?
So
I hate carrying.
one thing you can do is just get really fast at something else so you can take your time with this part. So So you make sacrifices here and there. You have to buy the bullet somewhere. So at the end of the day, now, if I plug in 1, what am I going to get?
He's fine.
So if I plug in 1 here, that'll give me what? That'll give me 0, right? Because I would have 2 minus 2. If I plug in 1 here, I'm going to have sine of n pi, which gives me 0. If I plug in 1 here,
You get 4 over n pi.
minus, according to the fundamental theorem of calculus, plug in 0. That first term is going to give me 0. That is going to give me a sine of 0, which is again going to be 0. Plug it in here. Cosine of 0 is going to be 1. And I'm subtracting a negative, so this is going to become a positive 4 over n. And again, that you realize will break into even and odd. So when your cosine is even, it's going to give you 0. And when your cosine is odd, it's going to give you 8 over n cubed pi cubed. So, ultimately, the original function that we were given can be expressed as a Fourier series of the form. Only looking at odd ends, n is odd, of 8 over n cubed pi cubed sine n pi x.
Why is that one, the 8 over n cubed pi cubed, positive? Because it's minus 4 plus 4.
Because when n is odd, cosine of n pi gives you a negative
Negative
1.
one.
Negative 1 times negative makes it positive. So
I
you get
see.
a 4 plus a 4.
Could n the indices or the index be at 0?
Yeah, or you could do something like, if you want to actually write down a bona fide series. And if it bothers you to rewrite it with n, you could just change a dummy variable and put in k
Put
instead.
it to 0
And
instead
then
of
put it
1.
like 2k minus 1 cubed pi cubed sine 2k minus 1 pi x.
Could you start k from 0 and then just do 2k plus 1?
You could also do that. That would be equivalent.
Yeah.
But we have
That's a
to-
matter of shifting. And that's those will all give you the same sum.
We have to say specifically that it's only for odd ones that the series works,
Yes.
so we can't just write 0 to infinity, and, because it would still be true, it's just some of those.
Yeah, you'd just be adding 0 infinitely often.
Yeah, but that's not
No,
okay.
I need you to identify.
Okay.
I'm kind of confused on what you're doing after with the even and odd, like how do you get 0 and 8?
Because it is a known fact that cosine of n pi is 1 when n is even. And cosine of n pi is negative 1 if n is odd. Right? We know that from the cosine graph.
Okay.
Right? At 0, it hits 1. At pi, it hits negative 1. At 2 pi, it hits 1. At 3 pi, it hits negative 1. At 4 pi, it hits 1. So notice that 0, 2 pi, 4 pi, 6 pi, 8 pi, it's at the peak.
Got it.
And at 1 pi, 3 pi, 5 pi, 7 pi, blah, 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 it's at the valley. So I know in the even case, it'll hit me, I'll be on top of the hill. In the odd case, I'll be down here. So it'll change to plus or minus 1. So you could even think of cosine n pi as an alternating thing, where n is empty. Because 2k plus 1 is always odd. It's just a way to express the fact that I'm only going to get odd things anyway. So instead of me writing down a sentence saying, oh, by the way, n is odd, I can just write 2k plus 1, and then everyone's going to, oh, it's only going to be odd.
So either one works. So if you were to write the top one, it's going to be odd.
Yes, that's why I bought both of them, because I would accept either.
Gotcha. Is one preferred? Like, in I guess you said the second one would be the preferred answer if you were like writing a paper or something.
It depends on the audience. I think that's the examples. I mean, that's probably the hardest you'll see something. You'll get an integration like parts thing. So all you need to know for Fourier series, really. How to compute one. Know if something is odd or even, you only have to do half the work. Otherwise, you might follow these formulas. Now I'm going to talk about, I'm going to try to set the stage for the next, well, not even setting the stage. I'm just going to do some preliminary computations that we will start with on Monday and do something really cool with it. It's also cool because it's going to have us review some linear differential equations, which is, I guess it's good. At this point, it should feel like kicking everyone. So, there's something called the Sturm-Liouville theory. The whole point of this theory is to study one particular kind of differential equation. It studies differential equations that look like this: d dx of p of x dy dx plus q of x y equals lambda r x y, where lambda is a constant. So, there's a whole theory that goes into the applications and solutions of guys that look like that. We'll care about one of these. Sometimes it's kind of strange when you realize the things that people are studying. Like you can spend your whole life studying that equation. Like it was the greatest work of Sturm's life. No, Sturm and Liouville, they actually did a lot of contributions. They do a lot in complex analysis as well. Okay? We are interested in a very specific case. The case where p of x is 1, q of x is 0, and r of x is 1. So we care about solving things that look like y double prime. I think they put it minus. Because it works out nice in calculations later. So y double prime plus lambda y 0. This is one particular kind of equation. This is called an SL problem from Sturm-Liouville. SL problem. So we want to look at solutions to this differential equation. You will realize next time it's super important that we're able to solve something like this. Also, with particular initial conditions. Namely, we're going to look at all such differential equations where y of 0 is 0, and for some particular L value, to be suggested when you wait, it will also give me 0 at this future value. So, constant of particular interest. Now, for those of you in 392, have you started looking at eigenvalues and eigenvectors yet?
Yeah.
Okay, so the solutions to this they're called eigenfunctions. And the lambda solutions are called eigenvalues. And the reason they're called that is from the linear algebra part of it. What you'll realize is it kind of looks like we're saying y double prime is some constant times y. So if you can think of the derivative as a differential operator, basically I'm saying there's a matrix that describes a derivative times this vector just gives me a constant times the vector, right? So it looks kind of like an eigenvalue, eigenvector problem from linear algebra, and so we call these, the solutions are eigenfunctions, and the constant solutions are eigenvalues, and those of you who know about this already know that that's a super important thing to be able to solve, the eigenvalue problem. Stretches far and wide. I guess one of the most cool examples that the kids like is Google. Google exists. Google has made Google because of the eigenvalue problem.
Wait, what? Can you explain it?
Well, I could, but
I mean, not in that.
that's going to take like...
Google.
Yeah, I mean, just like, what do you mean?
I actually did it in one of my classes this semester, in my finite math classes. We talked about something called Markov chains, and we talked about something called the stationary matrix. The stationary matrix was really an eigenvector of this matrix equation that I taught them about. I didn't tell them that way, but that's what it was. And basically you could use that to find the quickest path. If you have like a graph, you know, like a bunch of nodes connected, you could find the quickest path, or where a lot of things, if you just drop them and they're randomly moving around the graph, where would most things end up? And it turns out Google said, hey, we can organize a search engine around that. You put in a search term, we think of the World Wide Web as literally a web, right? Where websites are just interconnected. And then they kind of use an eigenvalue problem to figure out, if someone types in a search term, where would most people go? Make that search result 1. Where's the second place where most people go? Make that search result 2. Whereas before that, search engines were just like dictionaries. Like you typed in a search term, it just literally found every website with that search term and plopped it on a page, and like you do the sorting yourself. Google figured out how to make the internet do the sorting. Just kind of figure out where people are going, and if most people go somewhere and stay there, like if everyone who goes to the search term, they go to this website and they spend like 30 minutes there. That's probably useful. Let's put that at number 1. And then that's why after a while, everyone stopped using all the other search engines and started using Google. And that's because most of these computer scientists just, hey, let's make a dictionary and a web crawler and let's just plop everything down. And then Sergey Brin and Larry Page were like, hey, you remember that thing you learned in linear algebra class? What are you talking about? Dude, Markov chains. Man, we're never going to use that in our lives. Like, no, dude, for real. I think we can organize our search engine this way. Billions of dollars later. Now, Google is synonymous with search, and the reason is eigenvalues and eigenvectors.
Is this like the traveling salesman problem?
Just Google it. Like when someone says just search for it, they just Google it. And Google is Google because they imagine the internet as an eigenvalue problem.
Is this like the traveling
That's oversimplification, but I actually kind of constructed how it would work in theory for my kids in finite math. Anyways, so let's go in. Yeah. And yeah, the theory that they used to actually build Google existed for like 100 years, but no one thought about it because everyone thinks, oh, you learned that thing in school, you just forget about it. No, you'll be surprised. You could have something that you studied in calculus class and go off and make $1 billion business one day, just because you decide to look at a problem creatively, instead of just, forget about it, I already passed the class. So, let's actually solve this problem, which I think I have there. We're actually over here. So, that problem isn't particularly a difficult one because it's just a linear second order with constant coefficients. We know how to deal with that. The problem is we don't know what the lambda is. So we will just break it up into cases. 1. We can consider the case where lambda is a negative number. Or, which one do I want to do first? Yeah, I think negative 0 and 3. Lambda is a positive number. Okay. So, let's go through these. So we have y double prime. If I move this plus lambda y equals 0. So now, what's going to happen if we're in case 1 and lambda is negative?
Then y double prime is equal to.
So we do r squared plus lambda, right? Is going to be 0. So your r is going to be minus lambda plus or minus square root.
Would be r squared minus lambda? Because lambda is negative. R squared minus lambda.
I don't know what you're talking about. So it's we're solving this guy, y double prime plus lambda y.
Yeah, but lambda is negative, so wouldn't it be
Yeah.
y double prime minus lambda y?
No, it's still, it's just plus a negative. I just know in my head that this is negative. I don't have to necessarily use a negative sign to represent it. So you'll move to the other side, you take the square root. If this guy is negative, if lambda is negative, then negative lambda is actually positive, so this is a real solution. So we have two real solutions.
If lambda's positive, we're going to get an imaginary.
Well, but let's deal with the real solution. What would our function look like? What would our eigenfunction look like?
C1.
C1,
E to the negative, E to the
it's a negative lambda.
E to the
Square root of negative lambda?
square root of negative lambda times, let's make it x, plus c2 e to the square root of negative lambda times x, right? That would be our solution. Now, if I want y of 0 equals 0, and I want y of L to be equal to 0, this means if I plug in 0, I would get c1 plus c2 equals 0. And if I plug in L for x, I would get c1 e to the L radical minus lambda plus c2 e to the L radical minus lambda equals 0. What's that solution? So here, you know that your c1,
Are those two terms the same? Also,
C2x.
there should be a minus.
Yeah, okay.
Yep. So we have c2 is going to be negative c1. So plug that into the second equation. That would mean that c1 e to the L radical minus lambda minus c1 e to the minus L radical minus lambda equals 0. This means c1 is a constant that I can factor out. And what are you going to notice?
How'd you get a positive?
There should be minus.
You could just add the
Zero.
power.
What's going to be 0?
The exponent?
Is this ever going to be 0? It's possible for this to be 0 if we assume the power is 0.
Yeah.
But if you have a 0 eigenvalue, then your eigenfunction will be 0. Not very interesting. And the L, you want it to be a non-zero number. You in fact want it to be a positive number. So this is e to some positive power minus e to a negative power. They're never going to be equal. There are complex solutions, but there are no real solutions. This is going to force c1 to be 0, which forces c2 to be 0, which forces your y to be 0, which is not interesting. This is a trivial solution. It's trivial. Okay, so we don't care for this situation. So let's look at case 2.
That's also trivial.
So in this case, the eigenvalues and eigenvectors will be 0, which that's nothing. Okay, that's a 0 solution. Who cares about that? In
Sorry.
case 2,
in the general solution, sorry, those are x's in the exponent,
where?
next to the square root of lambda.
From this point on, there are no x's. That is a lambda.
No, above, way up top.
Way up top, yes, there's our x's. That's the independent variable. So y is a function of x.
Yep, yeah.
Yeah. If our lambda equals 0, what's going to happen? Well, this means our y double prime plus lambda y equals 0. But if I plug in 0 here, that just means my y double prime equals 0, which means my y is going to be,
First degree polynomial in general.
Power k root.
right, a linear function. Now, if I plug in my initial conditions, and we'll see why I care about those initial conditions specifically on Monday. So if y of 0 equals 0, and y of L equals 0, this means, if I plug in 0 for x, C1 plus 0 equals 0, and C1 plus C2L equals 0. But if C1 equals 0, this means that C2L equals 0, and so your C2 must be 0. Because, again, we're assuming our L to be non-zero. So, again, the solution becomes y equals 0, becomes the solution. This one is trivial, not interested. Right? Now there's the final case. I'm going to get something, I hope I can get something. Now, in the final case, if we assume that our lambda is positive, so case 3, lambda is positive, and we have y double prime plus lambda y equals 0, then our characteristic is going to be this guy, which means r is going to be plus or minus the square root of minus lambda, which is plus or minus the radical of lambda times I.
Complex roots.
So we have complex roots. Now what's going to happen? This means your y is going to be C1
Cosine square root lambda.
cosine of
Positive.
Positive,
Or it doesn't matter.
square root lambda times x plus C2
Square root lambda sine.
sine of square root lambda times x. Now let's plug in our initial conditions. Y of 0 equals 0, y of L equals L, 0. So, if I plug in 0 for x, what happens?
C1.
I get C1 equals 0. Okay, so now plug in the second initial condition. If I plug in L everywhere, what's going to happen? I'm just going to have C2 sine of radical lambda L
Equals 0.
equals 0. Now,
Where's the other term go? Oh, yeah, okay, I see.
so now, does C2 have to be 0?
No.
It turns out C2 is not necessarily 0 here, which is good. Which means if I want to not have a trivial solution again, all I need to do is make sure that this part is 0. This times this equals 0. It means one or the other has to be 0. I do not want C2 to be 0 because that will just make y 0, which is uninteresting. So I'm going to force my C2 not to be 0, so that means the sine function has to be 0. Now, if sine of radical lambda L equals 0, what does that mean for radical lambda L?
It's multiple of 2 pi. It's multiple of like 0, 2 pi, 4 pi.
Yes, so what's a nice way to write that down?
Pi over 2? I'm sorry, pi?
Or 0.
Yes.
2n pi. Arc sine of 0.
N pi,
Oh, and
where n is any integer.
And the silence in my
Maybe you guys should do that whole 2k plus 1 thing. You guys really have to start thinking about the kinds of numbers that will lead to a certain outcome.
Is it anything what?
Any integer. Every multiple of pi, sine is 0 at every multiple of pi. 0 plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. Your sine function hits 0 at all of those. Which means, can I solve for lambda? My lambda is going to be n pi
N pi over L.
over L.
That looks familiar.
It is starting to. Hold on. Well, okay. So, all right. So, what does this mean, though? This means our solution, our general solution, is C2 times the sine of radical lambda times x, right? But if I now plug that in for this, sine of n pi x over L.
That's a lot.
Where have we seen that before?
in my 48.
That's very interesting. Okay, so now, So now what do we have? So those are going to be our so this means our eigenfunctions for this particular kind of differential equation, they will be functions that look like sine of n pi x over L. And our eigenvalues will be values that look like n squared pi squared over L squared. And we'll cover that on Monday. We're going to see what we're going to do with this. And you can already tell that a Fourier series is going to be involved somehow.
Wait, wouldn't there be anything in front of sine?
Huh?
Wouldn't there be any constant in front of sine or not?
Yeah, but you don't, it's like you ignore the arbitrary constant. You're just looking at the function. So that's like your y1. So the only interesting solution to this weird differential equation that we considered was this one. All the other solutions are just zero and not interesting. But there comes a point where to not get a zero solution, you get a sine solution that looks awfully like a Fourier series sine component. So we're going to
be from undetermined coefficients.
yeah. So Monday we're going to finish what the last one.
I was just saying, for the test, is it up to 48 series or is it up to
it will be up to here, and the bonus will be on what we do on Monday. But again, I'll post the review.
Is the final cumulative?
The final is cumulative, yes.